based on this, so please remember the expression for the high frequency voltage gain V0 by Vc is as shown, and based on this we have a problem here. Find the midband gain AM, the upper 3 dB frequency FH of a common source amplifier fed with a signal source having RSig 100K and amplifier having RG 4.7 mega and RDRL 15K. So GM, R0, everything is given. First we'll find the midband gain AM, which is minus RG by RG plus RSig into GM RL dash. And RL dash, how do I find? Parallel combination of R0, RD and RL, which is 150 parallel with 15 parallel with 15K, which will give you 7.14 kilo ohms. And then GM into RL dash, GM is given as 1 milliampere, 7.14 volt per volt. Finally, AM, the midband voltage gain will result as minus 7. Okay. When I divide RG, which is 4.7 meg, a large value, with 4.7 meg plus 100K, this 7.14 becomes 7 volts. Then C equivalent we should find, which we determined is CGD into 1 plus GM. So here this C equivalent, we'll get it as 3.26 picofarad. Now the total input capacitance C in is CGS plus C equivalent, which will turn out to be 4.26 picofarad. Okay. So the upper 3 dB frequency FH is given as 1 by 2 pi C in into RSig parallel with RG. We had derived this. What is this? RSig dash we call it as. Okay. So RSig was 100K in parallel with 4.7 mega, which will be a value close to 100K. So you will get the upper cutoff frequency as 382 kilohertz. Similar to this problem, I told you there is another problem. If you change the source resistance to 10K, instead of 100K here, if you have 10K, the denominator here will reduce to 0.01, right? 0.01 parallel with 4.7 mega. So I'll have 10, this reduces by a factor of 10. So you can expect FH to increase by a factor of 10. FH will be, instead of 382K, it will be 3820K or 3.82 megahertz. So decreasing this signal resistance frequency, decreasing the value of RSig will increase the upper cutoff frequency, which you can try it out. So next, let's move on to the low frequency response. We can do only part of this low frequency response today. I told you the low frequency response is this band. So in the frequency response curve, we are looking at this band now, the value less than the mid frequency. So here, what should I consider? I should consider this coupling capacitances CC1, CC2 and the bypass capacitance CS. All these three will come into effect whenever we try to analyze the low frequency response of amplifiers. Okay. So what happens now? I have considered the common source amplifier circuit considering all these capacitances CC1, CC2, CS. Remember, now I can't neglect them because they will not be completely bypassed or they will not be short circuited. Why they will not be completely short circuited? Because the frequency is less. XC, the capacitive reactance is 1 by 2 pi FC. If F is small, the reactance is high. So the capacitor cannot be replaced with a short circuit, meaning it has to be considered. At low frequency of operation, all these capacitors will have to be considered and they will affect the gain of the amplifier. So the equivalent circuit, anyway, this current source, removing all these DC sources, we have written second case. See here, all DC, for AC analysis, all DC sources act like short circuit. So this point will be grounded. Similarly, this current source will act like open circuit, so it's not considered. The rest of the circuit is same as this. For AC analysis, this is our equivalent circuit. Okay. Now, whenever we do the small signal analysis at low frequencies, we have to consider three cases. The first case is for the effect of this capacitance. So I'll consider the effect of this capacitance CC1 as the first case. In the second case, I will consider the effect of the bypass capacitance CS. And in the third case, we will consider the effect of the coupling capacitance CC2. All these three capacitances will have an effect, and all of them will result in different lower cutoff frequencies. Each one will result in a different value of lower cutoff frequency. So it is like you will have the response something like this. Okay. See, this will be one lower cutoff frequency, another third one. Three lower cutoff frequencies due to three capacitors. CC1 will result in one value. This CC2 will result in another value, and CS will result in another value. All the three will have different effects on the behavior of the low frequency response of the amplifier. So we have to consider each one separately and analyze. So what we'll do, we'll use this, what do we say? We call it superposition theorem, right? Consider the effect of one element at a time and neglect the other two. In the end, we'll add up all. We'll consider the effect of all the three together and add up. So we'll be using the concept of superposition. So first, I will consider CC1, this part of the circuit. So in the next slide, you can see I have written only the beginning part of the circuit, where I have the signal source, its resistance R sig, CC1 the coupling capacitance, and RG the resistance. Okay, the biasing resistance RG. So we have to find the effect of this first. So to find the effect of this, I will consider the voltage across this RG, because this is the output for this part of the circuit. What is that voltage? It is VG. So this voltage VG will be determined as V sig, this signal source voltage, into RG, the value. We are using voltage divider rule. V sig into RG by R sig plus, remember, capacitive reactance XCC1. XC1 or XCC1, the reactance of this capacitance, plus RG. So R sig plus XC1 plus RG will be the value of the voltage VG across this. Now, what should I do in the next step? So from here, you just come down here. From this step, come to this step. What have we done? We have divided the numerator and denominator with capacitive reactance XC1. Okay. So after dividing the numerator and denominator with XC1, what do you get? This will simplify to this. And instead of XC1, I am substituting XC1 as 1 by S into C1. So what will I have in the numerator? SC1 into RG, RG plus R sig into SC1 plus 1. So this will be the simplification. And now in the next step, I am continuing from here. Continuing from this point, you can see VG is V sig into RG SCC1 divided by RG plus R sig into SC1 plus 1. Now, I want to take RG into SC1 by RG plus R sig into SC1 as the common factor outside. So when I take this outside, what is left inside? In the denominator, I will have 1 plus, I have to divide this 1 by this whole factor RG plus R sig into SC1. You can see here, the complete simplification is shown. SC1 cancels out here. So what is left outside here? Vg is Vsig into Rg by Rg plus Rsig into S by S plus here. How did we have this S? So I have this, I'm removing S from here. If I remove S from here, I'll have S plus 1 by Rg plus Rsig into Cc1. And that same S, when it goes to the numerator, it will be here. So multiply and divide with S, you get this. So finally, what have we shown here? This equation has, this whole equation is in the form of a single time constant. Which filter? High pass filter. High pass filter is something which has a capacitance first and a series resistance like this. Okay. This high pass filter, what you have done in the lab, is just opposite the low pass filter. This is the standard response of a high pass filter. It will be in the form S by S plus 1 plus or S by S plus omega naught or omega h, whatever you want, you call it as S by S plus omega naught. It will come to this form, and that same form we have shown has come in our equation, and this will be multiplied by the midband gain or whatever separate gain constant. So we have just proved this. What I'll do, I'll stop for now and I'll give you I'll send the PDF of two things which gives you an analysis of high pass and low pass filters. Single time constant high pass and low pass filter analysis. I'll send you the PDF. Go through that. There we have shown that for a low pass filter, what we got before. Okay. For a low pass filter, we had got this expression. No, it will come in this form. It will be the gain divided by 1 plus S by omega naught. It will be in this form. And for a high pass filter, it will be in this form. Am into S by S plus 1 omega naught. So I'll just send you those documents. Have a look. And then in the next class, maybe for the first half an hour I'll take, we'll analyze this